video, I wanted to take a moment to go over how to do homework questions involving minimizing inventory cost. So this concept's really interesting, and I just want to make sure that it's not exactly intuitive how to handle this question. So I wanted to make sure to provide you with a good example on this. So this is a question out of the book. It's 3.5, number 47. In the current homework, it's number 12, but that can change from semester to semester. All right, so the question goes like this. A company sells 720 calculators a year. It costs $2 to store one calculator a year. So on average, it costs $2 to store a calculator a year. This just takes up inventory space, takes up space in a warehouse, whatever it is. Then for the company to order the calculators, it costs them $5 per order, plus $2.75, so $2.75 for each calculator it orders. So the question is how many times per year should the store order calculators, and in what lot size? Okay, let's start off with this. So we're interested in minimizing inventory cost. We'll create a variable for inventory cost. We'll call it C of X. And just to be very clear, we'll say X. X is going to be, well, one of the things we want to find out is about lot size. So X will be lot size. So this is, in other words, how many calculators we're going to order every time we place an order. All right, this just to give you an idea of what's going on here. There is an assumption, and the assumption is that you have a store, or this company's a store, and it sells 720 calculators a year. Now, most likely with calculator purchases, there's probably a big surge in people purchasing calculators at the beginning of every semester, or maybe in September, August of every year. But we're going to assume that the inventory looks something like this over time, where if they purchase 720 calculators at the beginning of the year, I'm sorry, that's not X, this is time, and maybe this is the end of 1 year. Okay, so the idea is if they purchase 720 calculators at the beginning of the year, they would use it all up at a constant rate. It's a constant slope. It's a linear function. It's not given that this is our assumption, but in the absence of any kind of directions, this is what we're going to have to assume. And the idea is like, for example, at the halfway point, right, the slope is essentially, the slope is negative 720 over 1. So halfway would be 360 if we were halfway. My scale's a little off here. And a quarter, the way would be 180, et cetera. Okay, but there's a reason why I did that halfway mark. Okay, so one thing that we're going to have to figure out is it costs us money to store these calculators. And so it costs us actually $2 for every calculator we store. So if we have 720 calculators, it would cost, and we had that throughout the whole year. So if we just had like 720 calculators as our inventory, and it was that the whole year across, then so at the end of 1 year, we started off with 720, we ended with 720. This would cost us a total of 720 times $2 per calculator. But that's definitely not what's going on because we are selling the calculators. So in this first scenario, where we started off with 720, we sold about 2 calculators a day, and at the end of the year, we have no calculators left. Then on average, we would have 360 calculators. On average, we're going to be halfway. I hope that kind of intuitively makes sense. We'll explore average values of functions towards the end of this course, but hopefully kind of intuitively, this makes a little bit of sense. All right, that's fine. Another option would be, let's say we had 2 batches of calculators. So the idea is that halfway throughout the year, we're going to reorder calculators. So then we would need each batch that we order to have a height of 360, because then we'd still have we'd still order and sell 720 calculators throughout the whole course of the year. But the idea is we order 360 calculators, we sell them, then we order 360 calculators again and sell them. And in this example, on average, we'd have half that. Okay. So putting some letters to this is mostly using your book notation here. They call X is the size of the batch order. So the average amount that we have in the inventory would just be X over 2. So if our batch size was 360, our average inventory would be just 360 over 2, which is 180. So hopefully that makes sense. So this is an example where we have one order a year. This is an example we have 2 orders a year. It might even make sense for us to have 720 orders a year. So in other words, we're not going to order a calculator until we sell the previous calculator. The issue with that, where that sounds wonderful, is this fixed cost. Every time we place an order, it costs us extra money. So we clearly don't want to be in this first scenario where we have one order a year and our inventory is going to be really large. Our average inventory is going to be 360. But we probably don't want our orders to be just one calculator at a time either, because we're going to have to pay that inventory. We're going to have to pay that order fee every time. So we want some number between those extremes, and we have to figure out what that is. All right, so now that we have the basics set up here, let me give you some formulas to work with. Okay, ultimately, we're after C of X. Well, we want to minimize this. We want to minimize the inventory cost. They actually don't ask us what the inventory cost is, so we're not really directly interested in this number, but we want to minimize C of X. And C of X is going to be the carrying cost plus the reorder cost. So when we talk about our inventory, there's going to be a cost to carry it, basically the cost to hold the inventory, and also the cost to order the inventory. So we're just separating those two costs. Hopefully that makes sense. Let's break this down. All right, so carry cost, let's start there. I'm only starting, there's not one right way to start. I'm just starting here because of the first word I wrote. Okay, so the carrying cost is going to be our yearly cost to hold each item, to store each item, times the average number of items that we're storing. So basically the average inventory size. Let me phrase it that way. Okay, so let's see if we can figure out what these things are for our question. I'll use a different color. So our carry cost, I'll use CC for carry cost. So carry cost, the first part of our equation here, is going to be the yearly cost to store each item, which they told us here was $2. Okay, so it's going to cost us $2 to store each item. Times the average inventory size. Well, we figured out if we assume a linear function that the average inventory size is just X over 2. Okay. We can simplify this, and this won't always be the case where it simplifies so nicely, but it does in our example here. So it only will happen when the average cost of store is $2. But the 2's will cancel, and we'll just left with X. So our carry cost, this part here, is just X. Okay, let's work on the next part. Our reorder cost is just going to be the cost of each order times the number of reorders. Okay, let's figure this stuff out. Okay, so we'll call reorder cost RC. Why not? Okay, so the cost of each order. Well, they told us here that it's 275 per calculator for each order. And we figured out that each order, we're going to order X calculators. We're going to order maybe 360, 720, 180. We don't know the number yet, but we're going to order X, right? X is the lot size. So our cost of each order is going to be the 2.75 times the number of calculators plus that $5. Because remember, there's that $5 fixed cost, what they're calling a fixed cost, but maybe it's a shipping cost, something like that. There's some fee, handling fee for us to place an order. Okay, we have to multiply this by the number of reorders. Okay, we can figure this out in terms of X. So in this first example, if we only did one order, right, it was just our X was 720. Here, when our X was 360, we had two orders, right? Well, we can work backwards. So in other words, if we know what X is, and of course we know the 720, which is the total number of calculators we want, we could figure out the number of orders just by dividing the two. So in other words, we know that 720 is the total number of calculators that we want to order over the course of the whole year. And we know that our lot size is X. So this should tell us the number of orders that we need. Maybe it might make more sense to look at it this way. 720 has to be the number of orders times the size of each order, because in total we need 720 calculators. So if you divide both sides by X, you wind up with this expression right here. All right, so let's go back. Okay, so the number of reorders is just going to be 720 divided by X. Maybe we can simplify this a little bit. Okay, so I'll just distribute. So 720 times 2.75 gives me 1980, I believe. And then 5 times 720 is 3,600. And we still need to divide that by X. In the first term, the X is canceled. All right, so so the reorder cost we figured out was 1980 plus 3,600 over X. All right, let's put all of this together. I mean, I already have it, just let's write it a little bit neater. Okay, so we have C of X equals the carry cost plus the reorder cost. So that was just X plus 1980 plus 3,600 over X. All right, looks good. We want to take the derivative. So just so I don't have to use the quotient rule, I'm going to rewrite this just so I have exponents instead of division. 3,600, well, divided by X is the same thing as multiplying by 1 over X. 1 over X can be written as X to the negative 1. So this will make it easier for me to take the derivative. All right, so let's take the derivative in order to figure out a critical value for X. The derivative of X is just 1. The derivative of 1980 is just 0. I don't need to write that. And then the derivative of this last part, you bring the negative down. You'll get negative 3,600 X to the negative 2, because we have to subtract 1 from the exponent. Okay, so we want to find where this is either undefined or equal to 0. Note that this will be undefined whenever X is 0, because we're dividing by X squared, but that would also cause the C of X to be undefined, so that's not valid. So let's just find where this is equal to 0. So I have 1 minus, let me rewrite this a little bit prettier. 3,600 over X squared equals 0. I think the easiest way, there's a few ways to do this. One of them, we can multiply both sides by x squared and then proceed. Might be easier just to add the 3,600 over x squared to the other side, and then essentially just multiply both sides by x squared to get rid of the denominator here. And I'm left with x squared equals 3,600. So now whenever you have something squared equals a number, you can square root both sides. Technically, you need to do a plus or minus on both sides. And you're left with x equals, let's see, the square root of 3,600 is 60. So our solutions are negative 60 or x equals positive 60. Obviously, negative 60 is not allowed. I didn't write the domain here, but clearly x, which was, remember, x was the, where is it, the lot size. Obviously, you can't have a negative lot size. Lot sizes need to be at least 0. In fact, it definitely has to be greater than 0 because we're ordering stuff. So the negative value is not legitimate. So that's our lot size. So we're going to order our calculators in batches of 60. And the second part of the question asked us, it asked us for the lot size and the number of times per year that we're going to order. Okay. So our lot size is 60, and we figured out the number of times per year that we should order, or number of orders per year. Let's just phrase it that way. We already figured this out before. It would have to be 720 divided by x. So it'd be 720 divided by 60, which is, let's see, 72 divided by 6 is 12. Okay. So those are our answers. We're going to order 12 times a year, 60 calculators at a time. Have we proved that this is a minimum? No. So the way we can prove this is a minimum is we can look at the second derivative. And if the second derivative is positive, that means the function is concave up, and that means it would be a minimum. But I mean, this is the only possible. I mean, it has to be this. There really is no choice. All right, so that's how you tackle this question.